Okay, let's take the next step in this question. The next step is, what is the temperature drop from the outside to the inside surface? So just as a reminder, we know that we have, in this situation, we have 400, hold on a second, we have 400 watts that's coming into our system. Here's our system right here of this tower where the light is being focused onto a plate on the tower. And we have 400 watts coming into that. And we know that that power is dissipated in either reflected light. Okay, so here's reflected light, in radiated power, and then power that is absorbed or transferred, conducted to some fluid that's behind here. So the power is coming in. Some of it, this is like a black body radiator, but not all of it. So it absorbs a great deal and it emits a great deal. Some of it's radiated away. Some of it's transferred and conducted to the fluid beneath. Some of it is actually reflected. So some of this incoming light is actually reflected. How much? Well, since the emissivity is 0.9, 10% is actually inside this term right here. So let's go and answer the second part. What is the temperature drop from the outside to the inside surface? I'm only guessing that what this means is this outside 500-degree surface to the backside where the fluid is taking the heat away from that front surface. Okay. Temperature drop. That's what we're trying to compute. Okay. Okay, so here's our equation. The 400 watts is equal to the reflected power, the radiated power, and the conducted power. And I wrote the equation for conductivity here, where the dq dt is equal to negative k times the area times the temperature gradient through which it is conducted. So this is sort of a one-dimensional, imagine this axis is x, a one-dimensional heat flux. You have a temperature, a high temperature here, a low temperature here, and you're transferring heat across this temperature gradient, and the rate of that transfer is proportional to the gradient through the conductivity and the area. Now, the question is, what is this delta T value from the outside to the inside? That's what you're looking for, this delta T. So, we take this equation, we know that, let's see, what do we know? Well, we're going to have to back calculate this. This reflected value, since the emissivity is 0.9, let's presume that leftover, this is all what's all absorbed, what's all emitted, that leftover, that 0.1 is actually what is reflected. So this is 0.1 times the total 400 kilowatts. Now notice this is one significant figure. So we have 400 kilowatts equals 0.1 times 400 kilowatts plus 40 kilowatts plus P conducted. Okay, so this is 1% of that, which is, what is it? No, 10% of that, excuse me. They get another 40 kilowatts. So 400 minus 40 is 320 kilowatts equals the P conducted equals dq dt equals negative kappa A dt dx. Now let's start to plug in some terms here. We know that 320 kilowatts times dx divided by negative Ka equals this dt, this gradient. This will be equal to 320 kilowatts. We know that dx is 5 millimeters from the problem. So I'm going to say 5 millimeters. 1, 2, 3, 5. 1, 2, 3, 0.00, is it 005? 1, 2, 3, 5 meters, 0.005 meters divided by negative K, which is given in the problem, 52 watts per meter Kelvin times the area 2 square meters equals delta T. Or equals, we'll call this T2 minus T1. Now notice we're going to get a negative number indicating that this is a lower temperature than this, and that's what we're expecting. So I have no room to do this problem, I see. Well, okay, 320 divided by 50 is, I'm going to call that 6. So we have, this is equal to 6 kilowatts. I'm going to say 6,000 watts. And let's keep track of our units here. This watts crosses out with that watt. 1 meter cancels with 1 meter here. We've got meters canceled here. So we basically have the Kelvin moving up to there. So let's see, we'll finish this math here. 6,000 watts times 0.005 divided by 2. Maybe squeeze that in there. Well, we got watts. We crossed out the watts. So this is Kelvin equals, now 10 to the third, 1. If I move this decimal place, as you can see, 3 places, 1, 2, 3. That gets rid of this guy. How come my color is not changing? Okay, gets rid of this guy. I'm moving this 1, 2, 3. So we have 6 times 5 divided by 2. So 30 divided by 2, roughly 15 Kelvin, negative 15 Kelvin. There's our negative sign, equals delta T. So the question is, what is the temperature drop from the outside to the inside? It drops by 15 Kelvin is the drop. 15 Kelvin. The drop is not a negative 15. The drop is 15 Kelvin. So I'll just write that somewhere up here. This is T. This is 500 degrees C minus 15 degrees C, or 15 Kelvin. So the T drop is 15 Kelvin, about 15 Kelvin. Now, I want to point something out. This is 2 significant figures. We really only have one. You can call this either 10 Kelvin or 20 Kelvin if you're not using a calculator.